Feldmann, who I asked for a sneak preview of this talk, and she told me that it was going to change our way of how we think about data. And I read in the abstract here that it's actually going to talk about mental models. So she thought that real data sets were impossible to verify and validate. I'll be interested to hear how the mental models go. Take it away.
Well, thank you very much for the invitation to give a presentation here. So today I want to talk about an opportunity for ISP and application collaboration. But in order to actually get there, I want to kind of first start with revisiting some of the traffic characteristics and what we know about them. And at that time, actually go back to those mental models and kind of question some of those. And then actually talk about ISP and peer-to-peer collaboration, some proposals that have been out there and are within IETF standardization, and then kind of see how can we actually extend upon that, because some of the reality shifts that have actually gone on within the internet traffic. And if there's any time, then we talk about some of the things that people may actually do with these nice mobile devices, and then kind of summarize. So, traffic characteristics. What does everybody think? Well, whatever you have is you have some kind of what is called a killer application. And basically, the kind of effect that this has is, if you look at the web, then in 1993, there was hardly any web traffic. Then just about a year or two later, kind of about 60 to 7% of all of the internet traffic was web traffic. Now the question, of course, is, what is the dominant application in the internet right now? So what is your idea? What is the dominant application right now? Depends. Good. So what is it? Video.
Where? In what area of the world?
Anywhere.
Video?
YouTube.
Talks of the Newton Institute.
Nobody talking about BitTorrent or something like that anymore? So let's actually go back in time a little bit. This was some data from AT&T traffic by port in terms of actually just looking at 18 hours of traffic. And you basically see that at that time in terms of bytes, World Wide Web was dominating. Then you had net news. Does still somebody remember what net news is all about? Then you had email, and then you had a few other kinds of things, but in terms of statistics, fairly small. But World Wide Web traffic dominated everything. Then in about 2006, when everybody was saying peer-to-peer is out there, there was a traffic mix back here at the University or the Technische University of Munich here, where you again had web out there. Now you may say, how come that is? Well, they were actually trying to limit how much peer-to-peer traffic the students were generating. And so basically all the student housing was shaped and all the popular ports for peer-to-peer were blocked. And so water statement is absolutely correct, it depends. Now this is a nice statistic that somebody put out there. And I remind you that you probably don't want to believe any statistic that you didn't falsify yourself. So keep that in mind. So in 93, it was kind of email and FTP, and then you get the web kind of rising to about 70%. And according to this, kind of in 99, 2000, peer-to-peer started and was kind of rising up to about 70%. So now we should be at 100% if we believe this. And if you believe some of the people that are developing some of these applications, they are saying they are going to control 99.9% of the traffic if you talk to them privately. Well, the question is, what is really happening? And so we wanted to actually go back and see what is happening within residential broadband access traffic. Why? Well, it is actually under-examined because there aren't that many data sets of this kind of traffic available. Most people have looked at university traffic and then trying to generalize from that. And so it also differs from that because there's nothing such as an acceptable use policy. Most ISPs allow you to do whatever you want to do, unless they are doing traffic shaping, because they don't want all that peer-to-peer stuff there. And of course, it's a precursor for a security threat analysis, which we have also done in the meantime. Here are some statistics about how traffic actually looks like today. And this is basically collecting the most recent various different data sets that are out there. So this is also shows some interesting shifts. So this is the IPAC study that we just looked at from 2007. This is the corresponding one from 2009. And here you see that web is increasing, and you also see quite a bit of BitTorrent in here. Now, here's the same study for the Middle East. Here is a study for ABA worldwide networking 2007 and 2009. And this is basically looking at NetFlow data using the port numbers in order to classify applications and basically looking at a huge portion of the total internet traffic, the traffic between ISPs, which they have access to. And then there's a Sandvine study back here. Now what you see is that web traffic here, just the basic web traffic, is already increasing to about 40 to 50%. In addition, you have quite a bit of streaming, and this streaming actually includes YouTube on top of HTTP. So it actually, quite a bit of that is also web traffic. Now, you also see that things like unclassified and eDonkey, etc., have gone down. And so one of the things here is that the ABA study said that peer-to-peer is most likely at something like 18%, and so substantially reduced. So if you compare that to this kind of prediction over here, and when you went with this kind of prediction about the dominance of peer-to-peer, you're probably wrong today. Now, the study that I want to talk about and kind of look at some of the data is actually this study over here, which says that you have about 40% pure web traffic, then you have about 20% streaming, and then you have the others on top of it, with less than 15 to 30% of peer-to-peer traffic out here. And if you look at the overall statistics, there are similar results from other kind of studies, and also the analysis of some of US-based ISPs has also given rise to similar results. So what is the focus? Well, we want to look at some of the broad range of dominant characteristics. So we want to look at DSL session characteristics, then popular protocols, and then some of the performance statistics. So DSL session characteristics. You might be interested to ask, why the heck should I care? Well, one of the things that is happening is that, especially for security analysis, people like to say, oh, this IP address is bad. And then they think they know who is actually behind this. So IP address equals user. But actually, if you go around and you kind of go back, reconnect to the internet, then you actually do get a new IP address. So whomever you are blaming at that time might be somebody completely different. And so that's why it's so important to understand how IP addresses are being used. So what I want to do next is talk about the data set and then look at some of these characteristics. So the data we are using is observation from about 20,000 DSL lines of a major European internet service provider. They are all in one area, and there's basically no traffic shaping going on. So whatever the people want to do, they can do. We're using the Pro intrusion detection system as an application level data analyzer. So we are using its capabilities. So we're not doing security analysis here. And we basically have access to various different traffic traces, some shorter ones, but covering a whole week, and then 2 day-long traces, both in September 2008 and April 2009. And similar results are true even for newer data sets that we've looked at in the meantime. So this is basically how the aggregate throughput looks like in terms of upstream versus downstream direction. Now you notice that there's a typical factor of between 1 to 8, 1 to 10 between the throughput that is going on in both directions. Now whether that is an artifact of the DSL bandwidth characterization data or the other way around, that the way that you're allocating capacity to the two lines is a result of this kind of behavior, well, we can only speculate about that. But you also see the typical time of day effects here. In addition to that, we actually had anonymized DSL session traces. for the corresponding to the timing of the other ones. And in addition to that, we had a 10-day trace in February 2009. Now let's take a look at DSA session characteristics. How long do you think that a single IP address is in use by a DSA customer? What would be your expectation about the mean or the median? 3 days?
1 month.
1 month?
1 year.
It really depends on the ISP, if they have enough IP address or not.
They have enough IP addresses in principle.
Depends.
Thank you. So, Redis is used for IP leases. So you get a new IP address for every session when you reconnect. There's a 24-hour session timeout, which is actually enforced by the ISP. So 3 days are impossible. But there's no idle timeout, there's no traffic shaping, and the access bandwidth is between 1 and 16 megabits per second. Now, this is what you get. You get a complete bimodal distribution here. One is at about 24 hours when you're looking at the median duration of the DSL line in use. And the other one here is rather short. So your mental models of the fact that it might be huge time periods is just wrong. Because what is happening is that due to some of the time-based tariffs that used to exist and that are still in existence, the default configuration of most of the routers is disconnect if idle. So we actually verified the error codes of the disconnects. And it's not being disconnected by the ISP. So you get a high IP address churn. So 50% of your IP addresses are assigned twice in 24 hours. Up to 5% of the IP addresses are assigned more than 10 times within a single day. So that's actually kind of scary, yeah.
It does depend on the ISP, like the
There
free
is-
France due to a static IP address.
Right. It depends on the ISP, but if your ISP doesn't interfere except for the 24-hour timeout here, then it depends on the pre-configuration of the routers that you can buy in that country. Let's take a look at the application usage. We already talked about your mental models of what people are using, but let's see how it's actually looking like. Now, most people that want to actually do kind of an analysis of the application usage, there's always a question on how do you actually detect the application? Because yes, typically you expect, for example, web traffic to be on port 80. But of course you can run a web server on any other port. And especially peer-to-peer applications, some of the other ones actually tend to run on arbitrary ports. And so there are many, many, many reasons why you might actually want to run on a different port than the one that you're supposed to actually run on. And so what we're doing is we're using our network intrusion detection to actually really do the application detection. So a network intrusion detection sits usually between your company or some subset of the users and the internet and is analyzing the traffic here in order to look for malicious use. But since malicious use often means app using a protocol, it also has a lot of application detection protocols in there. Now, what we can do with that system, we can also do a dynamic kind of analysis. So we can basically have a signature that is looking for some part of kind of, oh, this might be web traffic or this might be email traffic. And then actually look at, does the application actually correspond to the protocol specification? And you can run multiple of these in parallel, and then if you detect it's not that one, that is turned off, and you can actually then move on. And so there is validation of that kind of a signature, which is based on bidirectional traffic. And so you can actually have certainty that this is really the protocol that is being talked upon. So we actually use this dynamic protocol detection here, and we can pretty much classify 85% of all of the bytes. Of the remaining 15%, 3.6% are on well-known ports, but we don't have specialized analyzers for it. We also find that there are no dominant day of week effects, And we also double check the results with netflow data from other parts in the network, and also with the commercial deep packet inspection system at a different location, that we really see the kinds of application mixes here. Now, if you do that, then you find this kind of application usage if you're looking at it by hour. So in the middle of the night, you have about just less than 40% web traffic. During the day, you typically have about 60%, which is on top of HTTP. Now, why is this difference between the night and the day? Well, during the day, you have more people that are active, so you have more kind of a user-induced kind of traffic than in the middle of the night, when some of the automatic stuff, just by proportion, is larger. Then you have some amount of BitTorrent traffic on top of it, some amount of eDonkey. Then NNTP. What the heck is the Network News Protocol doing here? I thought it was dead. Binaries, yeah. There are actually commercial services out there that are based on NNTP. So if you look at NNTP, it used to be there to be exchange of news and messages, but now there are actually P-based NNTP servers out there. And basically 99% of all that NNTP traffic is really binary. And so they augment the one-click hoster business in order to really offer some of that content that was available via file sharing. So that is what is going on here. And then you have some other things that are basically unclassified. So even if you take that unclassified plus that eDonkey and BitTorrent traffic, you're only getting up to about 30%. Now we can also look at it by different access bandwidths. And one thing you notice is that, of course, the users with higher access bandwidth actually use more bandwidth. But in terms of the traffic mix, it doesn't differ that drastically, except that the ones that are using more, that have higher access bandwidth, seem to be using the peer-to-peer protocols and also especially NNTP a bit more. So the key results are peer-to-peer is less than 14%, unclassified less than 11%, HTTP dominates. Port-based classification actually works very well because most of the web servers are actually running on port 80. So all those guys that are looking at using NetFlow to find out what their application mix is, you can use it. Seems to be working. There's streaming, there's NNTP, and there's some voice over IP.
You said the HTTP is including YouTube.
Yep.
The streaming that excludes YouTube.
That streaming here is the non-HTTP one that actually excludes YouTube, the 5%.
YouTube's included in the 5%.
Nope. It's non-HTTP. We'll get to that. Because one of the questions that we, of course, immediately asked is, why are people using HTTP? What makes it so popular again? So does it offer high volume content that people are interested in? Or is it actually app used as a transportation protocol? And so what we actually did is we looked at this anonymized HTTP header and looked at the content type and also used LibMagic to verify that. We also looked at the host name and the user agent to try to find out a better classification here. Now, what we have is popular content types by volume. And so, what happened here? This is what you get. Flash video, 25.2% of all the HTTP. That's your YouTube and other things like that. Then you have RA. Those are your archives. And if you look at it, and see that some of the one-click hosters are in the top domain, then you know where your RA archives are hosted. There's no significant hiding or tunneling via HTTP. And it basically, HTTP seems to be popular due to the high volume content.
The other is like text?
other or all kinds of different things, including text, including HTML.
What is RAR again? I don't understand what that is.
You know zip archives? RAR are similar, but more modern. Rapid share, for example, yeah?
HTML5, is that in the other or the Flash video? Where do you put HTML?
HTML is in the other.
Five, right.
Images are GIFs and JPEGs, etc. So let's look at some of the performance and path characteristics. So one of the things we wanted to understand was the TCP option usage. Is ECN used? What about window scaling? What are some of the performance limiting factors? What about loss and reordering? And also, how is that bandwidth utilization? Do these customers, are they actually limited by their DSL connections? Or what is limiting them?
Anja, just a quick question. Can I take from this that TCP is still by far the dominant?
Yes.
That's why you told me this.
Yes. UDP is certainly less than 10%. I believe even less than 5%, but I would have to double check that.
Which is what it's been like for years.
Yep.
So that's an invariant.
Yeah, at least at the moment. And I don't expect this to change because NAT is being deployed in more than 90% of the households that we're looking at, and getting UDP through NAT is kind of nasty. So I don't believe any trends that UDP is taking over the world.
How about multicast?
Forget about it. So selective acknowledgement is widely used. Explicit congestion notification non-existent. Window scaling is actually in use, but still the bandwidth delay product is actually greater than the maximum receiver window for at least 44% of the connections. So it actually, 44% of the connections that wanted to download more than 50K were limited by their windows. And basically, most lines only use a very small fraction of their bandwidth, even if they are active. Now, here's an interesting one, and that is in terms of the achieved flow throughput per application. And so notice that this is the probability density from the empirical data. You have a logarithmic scale, and you have a correspondingly scaled probability distribution back here. And you notice that eDonkey and BitTorrent are sitting back here, HTTP and NNTP is sitting back here. That's more than a factor of 10 more throughput. So that's a substantial better throughput. Now, you may say, oh, but BitTorrent and eDonkey are opening so many parallel connections, so they are making it up via that. No, they don't, even if you actually do it on a per session basis. So most lines use only a small fraction of the bandwidth. The throughput differs by applications, and HTTP and NNTP achieve a really substantial improvement. And pretty much NNTP uses even a larger number of parallel flows and is really doing well with it. So let's take a look at ISP and application collaboration. So at the time when people were saying that, oh, peer-to-peer traffic is making up to about 70% of the traffic, that something needed to be done about peer-to-peer. Remember this plot here? That was a nice motivation for this kind of work here. So if you look at it for peer-to-peer, it was good because it was filling a void as an application. Peer-to-peer and all these overlay applications are really easy to deploy and to develop. It seems to be spoiling the broadband demand. However, it's also bad because basically what you have is you have an ISP which has a routing system, and then you have an overlay which is also creating a routing system. Now you have two control systems that are interacting with each other, and I think Tim will certify that whenever you have that, you might actually get into trouble. And basically, traffic engineering is quite difficult with that. So ISPs are in some sense in a dilemma. And one of the reasons this is the way is, if you look at it in the internet, for the user it doesn't cost more whether you actually download your data from Australia or locally here from Cambridge. It's the same price. But when you're ordering furniture, let's say from one of these nice Swedish manufacturer, you would probably, when you're locally here in Cambridge, never think about ordering it from Australia because you would have to pay so much more for shipping. And actually that traffic really has to go that distance, and so it actually costs you more for the ISP that is operating this. And so the idea was that actually what should happen was that ISPs and peer-to-peer should collaborate, because the ISP actually knows its network, and it could offer something like a provider added distance information, which basically provides some amount of distance hint. So you can give it a range of different IP addresses and your own IP addresses, and then it would say, the distance to that one is actually nice at the moment. And distance doesn't mean physical distance. It could be bandwidth, it could be round trip time, it could be within the AS or external to the AS. None of this is only about keeping traffic inside one's AS. There are many more traffic engineering questions related to this. And so you could actually use that to actually build your neighborhood. For example, when you had kind of a user back here, and you might have the opportunity of downloading something from here, 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 or here, then probably the best peer to actually download the data from might be this one here, because it has a nice upstream capacity of 4 megabit here, and there's a 10G link between them. On the other hand, it might be that actually, you don't really care about the 10G link. In some sense, your limiting factor is the access bandwidth, and so this peer over here might be much better. But you know what? If this link is fully utilized with 100%, then you certainly don't want to go across that one. Then maybe you're even better off downloading and accessing the data from here, depending on your current network connectivity here. And that changes dynamically. And so you can either have the peer-to-peer protocol trying to actually infer the current throughput that you can get, or it could actually work together with the ISP that has to have this data anyhow. And so this is actually what is currently under standardization within the IETF-ALTO working group. And you can actually do nice kind of fun things when you have this kinds of data sets. And one of the things is that we can actually try to draw pictures out here when you do either random neighborhood selection, then you get these kinds of clumps of graphs, or when you actually try to localize the neighbors within the ISP, and then you can actually see some of the topology and know you're not going to get disconnected graphs. And what is happening is, the idea is that there's a benefit for the peer-to-peer system, because they don't have to infer information that is available to the ISP, and they can actually get better performance. And the ISP can actually do some amount of traffic engineering, and therefore actually reduce the link utilization on some of them. And also, contrary to actually looking at caching approaches, you don't cache the content, and therefore you actually have not so many legal problems here. You're just redirecting, and not all of the content necessarily has to be peer-to-peer or illegal peer-to-peer, so that even if somebody goes after this padded system and asks them, oh, give me all of the IPs that queried it, it doesn't necessarily mean that they were evil. Now, but peer-to-peer is going down. So should we just scratch all of this work? No, the idea is that we actually don't have to scratch this. And this is now the new kind of idea that I want to introduce here today. We've seen, if you look at it, the ISP really knows its input, its network, etc. And basically the PADIS concept, which is taking a list of possible destination IPs and ranking them, is actually applicable to wherever there is a choice. That means whenever content is available from multiple different places, you could use this kind of idea. Now, where is there a choice? There's, for example, a choice when you're looking at content distribution networks. There are some content distribution networks, and this is for one specific one, which, for example, has more than 3,500 caches distributed throughout the whole internet. So it's basically more than 3,500 caches. And if you want to actually download some file that they are hosting, you can actually ask any of their caches and it will return it to them. And so what we did was actually deploy a few PCs within some people's homes and actually download specific files, for example, this 510K big file from all of these 3,500 caches, and at the same time asked the CDN from which IP address should we have downloaded this file. And so what you see is a box plot for each one of these downloads. And then the line which is here in the middle, the CDN selection, is the one that the CDN would have actually recommended to use. Now the box plot gives you kind of the first quartile, the third quartile, and the median as the line back here. And then you have the outliers both in the positive as well as in the negative way. Now if you take a look at it, you notice that what the CDN recommends you to download things from is not always the optimal one. You can actually gain up to a factor of 3 in terms of user performance if you would actually download it from the one that is, in some sense, the best one. That is substantial. So just because you're downloading things from a CDN doesn't necessarily mean that the CDN is actually optimizing for user performance. The CDN has to optimize for reducing their cost. So keep that in mind. Now, where else is there choice? We saw that there's more than 50% web traffic. Among that CDN traffic, among that one-click hoster, etc. And if you look at that, then pretty much anybody that wants to have a substantial web service out there has to have a distributed infrastructure, because otherwise they can't really sustain the load. So the question is, where do they have it in the internet infrastructure? Is it all in one location or is it in multiple locations? And so we actually took the traces that we had access to, looked at the top 2,000 locations or 10,000 locations out there, kind of the domains, and kind of looked at where are they hosted? And are they available via different subnets? And what comes out is that if you look at it, then the different subnets that traffic could be served from, when you're looking at the full domain name, it's about 30 to 40%. If you look at the second domain name, third level domain name, then it increases. If you look at the second level domain name, then it increases further. Why is that? Well, that is because the way that the DNS resolution system works, they are actually using the second part of the domain name to actually do the localization. Now, in addition to that, DNS doesn't necessarily always return multiple IP addresses, even though the content would be available at multiple IP addresses. But if you do the same resolution, just a few seconds later, you will get a different set of IP addresses. And if you also include that, then you're getting to the point where 80% of the traffic can be redirected to more than 2 different subnets in the internet. And so there's a huge amount of possibility when you're actually looking at the second domain, or if you're looking at this redirection, just the different IP addresses that are being returned for different DNS lookups. So what does this mean? This means we can actually do traffic engineering, but we can do traffic engineering in a different way. Instead of actually changing the routing, we can just change the source of the information. So we can actually manipulate the traffic matrix. And that way actually get control of more than 25% of the total traffic. So if you have an overloaded link over here, and you know that with the IP address that Akamai might be giving you or some other CDN, the traffic will be going through there, well, don't use that one, actually do the redirection to another one. And so you actually do get a fully new options in which you can actually do traffic engineering. Nice. We just changed our problem formulation. So instead of doing traffic engineering by changing routing, we're changing our traffic matrix. So how could you do that? Well, one way to actually achieve this is to basically have your provider DNS, which most of the clients are asking, and then the provider DNS will actually ask the external DNS for your lookup. Then it receives a set of IP addresses that can be ranked by the PADA system. Or you can actually go further. You could have the user kind of send the information to the PADA system. You could have the operating system send it here. Or you could even have the content provider first querying the PADA system for the information and then actually sending back the information. Now, of course, you may ask, is everybody using the provider DNS system? Well, they are. And you better do use your provider DNS system because all of the lookup that the content provider is doing is based on the IP address of your provider DNS. So if that IP address is somewhere in the world and cannot be localized, then the choice that you're going to get is going to be awful in the first place. And so if you do that, then you could imagine actually getting this kind of performance down here instead of getting that one which corresponds to the red line. And we actually tested this also with some of the one-click hosters. And yeah, you're going to see performance improvements. And so there's quite a bit of potential here. And I think it's going to be interesting to see how all of this is going to play out. And so in summary, this idea is that you actually use the information that the provider has. And we have a prototype of it running. And I think there's substantial improvement here to actually change your traffic matrix to do better traffic engineering. And with that, I'm open for questions. Thank you for your attention. Tim.
You know, that last scheme you showed gave a little bit of the feel of some of the schemes that I've seen people talk about with the locator ID split and using the mapping service to do that kind of thing. Have you thought about that, or? So this is the scheme that's percolating through the IETF.
Yeah, I know what you're talking about. Let me put it this way. This is a much more direct way of doing things because the providers, the content delivery service are already using the DNS to do that kind of traffic engineering for their own servers and doing load distributions and also cost optimizations. So it's a much more direct way of doing it. And so you're just with this, we are just piggybacking on what the content delivery platforms are already doing. But of course, that kind of remapping can also be done on yet another level further down, and so further increase the capabilities that you have.
Yeah.
Are you saying that PADAs would learn about the different kind of locations of the different content providers through just listening in on the DNS and working out what they are?
Yep, you can do that. The DNS system has all the information necessary.
Can you go back to the hourly, the usage in your first part? I was struck by, this is just residential?
Yep.
So in the middle of the day, it's being used. And this is like a weekday.
Yes, of course it's being used in the middle of the day. There are some people that may not be working. Or that may be working from home.
I often see peaks in the evening, but there are still people there during the day.
This keeps you peaking in the middle of the day.
Well, this is percentage, right?
Yeah, the actual, that's the numbers we're peaking in the middle of the day.
That's normalized. But yeah, of course, you have people that are starting to use it during the day.
Have you got an unnormalized version of the pretty colored bar chart?
No, I don't. Not here with me.
I'm just wondering whether we're actually seeing an artifact,
Um,
the denormalization process, and actually some of these things are staying
constants, such
So
as the n.
that peer-to-peer, etc., will stay much more constant. So some of that, its relative increase is, of course, somewhat of an artifact.
If there are no more questions, let's thank Anja again for a very interesting insight.